into searching. What's she eating? Well, nothing now, but I was eating some toast. All right, so searching. Let's talk about searching. We've already been searching before, right? We've already been doing linear search. Linear search, very common. It's awesome. You can't really do much better than linear search in a lot of cases. So for our needs, we'll say that we want to search for a specific thing in something. And we want to know if it exists or not. For example, does a given number exist with an array of numbers? We will use this version of the problem here. We can have variations where it's like which index, how many copies, whatever. But we'll keep it simple. If we want to write an algorithm to solve this problem, all we really need is something that tells us if it's there or not. That's all that's required. We can write any algorithm that works. Now, it doesn't mean that it's necessarily a good algorithm, but if it gets the job done, it gets the job done. The algorithm solves the problem. So, just to reiterate, the point I'm making is, if I want to know if a given thing exists inside this collection of things, I just need a way to tell me if it's there or not accurately. How it goes about doing that, whatever. But we're going to look at two intuitive ideas that all of you have more or less used one way or another many times in your life. A linear search, or something called interpolation search, which we'll discuss a specific kind of interpolation search called a binary search, but you've all done this whether you like it or not. But you've also done a linear search, and this is the more obvious of the two. Throughout this topic, the thing we're going to be looking for is going to be referred to as the needle, and the collection we're searching will be referred to as the haystack. So we're looking for a needle in a haystack, okay? Just to get some nomenclature down. Any questions before I carry on? I'm just setting up the whole searching thing. Man, it's shocking that only 20 students are here out of like 50, so that's concerning. All right, so linear search. We've already seen this many, many times. Oh, it's fine, Bilbo. So we have used linear search many times already. When do you see it start to get small? How small do you mean? Because, I don't know, 50 is a pretty small number. Like, yeah, next year for sure, but like under 10? Oh, that's rare. Under 10 is very rare. St. FX doesn't offer courses unless there's at least 8 students in it, with rare exception. Smaller than 50, next year you'll see smaller than 50. Right now, I think a couple people have dropped, so it's like 49. But it's still, like, you gotta understand, like 50 might not seem small, but compared to other universities, 50 for second semester computer science is shockingly little. Like, that's a very small number of students, which is a good thing for us. But back to content. Which CSI? Computer, do they really care? Good employers don't. Bad employers will. It depends on who's doing the hiring. So if you get hired at a place like, if your employer's like, yeah, but you didn't go to university such and such, you don't want to work there because they actually don't know what matters. What matters is, can you solve the problem? Are you good at the job? So that's why a lot of like computer science job interviews are very like intensive problem-solving-y interviews, not like your classic HR interview of like, tell me about yourself, right? It'll be like, okay, here's a problem, solve it. Here's a marker, here's a whiteboard, go, right? So if you can do it, they don't give a crap about what school you went to. So if I can get into Waterloo, should I go? It depends on what you're looking for, but this conversation is now getting a little outside the scope of today's lecture content. No, it's a waste. I wouldn't say that. There's a complicated answer to that question. Waterloo is a fantastic school, but what do you want to get out of your university? If you're looking for a name, don't go to Waterloo just because of its name. Go to Waterloo for the right reasons. Don't go to St. FX for its name. Go to St. FX for the right reason, you know? All right, back to searching. Okay, so we've used linear search. Start at the beginning of an array. Again, I'm using array. It doesn't need to be an array. It could be any collection. But start at the beginning and sequentially look at each element until we find a matching element. If we find it, then we conclude that it's there. But if we ever get to the end and we don't find the thing we're looking for, we can conclude that it's not there. But remember, the instant you find the thing you're looking for in the array, you know it's in there. But you can only conclude that it's not in there after you looked at everything. So if I look at the first element, it's like, if it's what I'm looking for, return true. If it's not, keep going. I can't make any conclusion yet. Never ever fall for that classic beginner, like, oh, if the thing I'm looking for return true, else return false. No. You can only return false once you've looked at everything, once you've iterated over the whole thing. So remember that. So notice that this description of the algorithm, though, doesn't go into any details. It's a very high level. It's very abstract, right? There's no code here. Start at the beginning and look at each element. If we find it, we're done. If we don't, and we get to the end, it's not there. There's no code here, though. But would you agree that this is basically an algorithm, though? I mean, it's a very high level algorithm, but I mean, it's an algorithm. We've also discussed the computational complexity of this. The worst case scenario, we look at every element in the array before we make a conclusion. It's linear, right? So if I have an array of n things, the best case scenario is, oh, the first thing I'm looking for is what I'm looking for. And you only need to look at one thing. Here's a giant list of 1 billion numbers, and I'm looking for the number 77. I look at the first element in that array, and it's 77. Done. I don't need to keep looking. If I'm only looking to see if it exists in there or not. I mean, if I want to know how many there are in there, I have to keep going. But if I'm only looking to find out if it exists or not, and I find it on the first try, I only need to look at one thing. But in general, we're not going to be looking at the one thing, right? In general, we're going to be looking, like, on average in the middle. On average, we're going to see, like, for every time it's the first element, it might be the last element. For every time it's the second element, it might be the second last element. For every time it's the third. And so on average, the element we're looking for, if it exists, of course, is going to be like in the middle of there, right? On average, right? Does that make sense? But remember that, I mean, if we have n things and on average it's halfway done, well, that's like half of n. But 1/2 is just a coefficient, and it's a constant coefficient. We don't care. And so it's dominated by the linear term. So the worst case scenario is we have to look at everything, and the thing we're looking for isn't there, so we had to look at all things. Best case scenario, it's constant time. And on average, it's going to be like n over 2 things I have to look at, but that n over 2, I mean, we can't generalize that for computational complexity, so that half is just, we throw it away. It's still linear. Any questions about this? Okay, in the above example, we know if something is or is not there, we would need to look, to know if something isn't, we need to look at all n elements, right? Is the number 16 there? Okay, 1, is that 16? No. Is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. No, there's no 16. Right? This might feel like, okay, why are we going back in time to first semester to talk about linear search? We've done this before a bunch of times, and you're right. But we're going to analyze it a little bit more thoroughly at this stage. So are there any questions before I carry on? Just throw it in the chat if you do. And try to keep it focused to today's lecture content. So below is a very generic implementation of a linear search on an array of type T. So it's literally generic. It's static because I'm imagining I'm putting this next to like my main method. Other than being generic, this should be very familiar. Iterative linear search. The thing we're looking for, the needle, the array of needles, or the array of type T called haystack. And then for I0, I is less than the length of the haystack, I++. If haystack at index I equals the thing I'm looking for, return I. So here I guess I'm not returning true or false. I'm returning the index of the thing I'm looking for. So if I find what I'm looking for at index I, return I. And I'm done. Otherwise, keep going. And then only after the for loop is done running, which would be after I've looked at everything in that array, That's when I conclude it's not there, so I return -1. -1 being that sentinel value that means like, okay, well, nothing was found. All right, this iterative implementation is also fairly similar to the high-level description of the algorithm. I start at I equals 0, the beginning of the array. If the element at index I is what we're looking for, we're done. Otherwise, continue and increment I. If we look at all the indices and we don't find it, we know it's not there and we're done. It's the same idea of right here. Start at the beginning and sequentially look at each element until we find it. If we find it, good. If not, keep going. Or if we get to the end, we can conclude it's not there. That's it. At this stage, at what are we now? 11 weeks in? At 11 weeks into second semester, this should be like, yep, like you should have a very, like this should be very clear to you. Now let's do a recursive version of that same high-level algorithm, but we're going to do it like with recursion instead of iterative. All right? So let's see. Remember with recursion, we want base cases and recursive cases. So let's look. Well, okay. What are we getting? Well, we're getting the thing we're looking for, type T. The array of type T called haystack. And we also are getting this additional value here, another parameter called current index. And current index is going to serve the same purpose as I. So like, which index are we looking at? So the first thing I ask is, okay, if the current index is equal to the length of the haystack array, return -1. So what this means is, if we ever get to the end, then it's not there, right? If we ever get to the end, it's not there. That's what this is saying. Because remember, if the haystack's length is 10, it's got indices 0 through 9. If current index is 10, there's no more places to look. So if it's not there, if we ever get to the end, return -1. Else, if haystack at current index is equal to the thing we're looking for, return current index. This is the same idea as right here. If the haystack at the index is what I'm looking for, return the index. If the haystack at the index is what I'm looking for, the needle, then return that index. But this is another base case. Notice that. This is a base case. So we have the base case. If we're at the end, return -1. If we find it, regardless of where we are at some arbitrary index, current index. If we found it at current index, then return the current index. Otherwise, do a recursive linear search for the needle on the haystack in the next index. So this might be a little crazy to look at, but think of it like this. If I were to start this here, which index do I want to start at? I want to start at index 0. So I would call this for the first time saying recursive linear search, needle haystack 0, where 0 is the beginning thing. So I say, let's think through this for a second. Current index is 0. All right, so is 0 equal to the length of the array? Well, unless the array is empty, that's not the case. If the array is empty, well, then we return -1 because, yeah, it's not there, right? If we have an empty array, is the thing I'm looking for in that array? No, because it's empty. There's nothing there. So that makes sense, I guess. But in general, current index is 0. The haystack is length, let's say 10. Okay, well, I'm not going to return -1. Now, if haystack at index 0 is what I'm looking for, simply return the index. Otherwise, return the result of calling this, but on the next index. So this would call this method again recursively, but now current index would be 1. So let's go up to the top. Current index is 1. Is 1 equal to the length of the haystack? No. We're saying it's 10. Is haystack at index, current index, the thing I'm looking for, equal to the needle? So check if it's what we're looking for. If it is, return current index. Let's say it's not. Otherwise, return linear search, and now call it with current index is 2. Okay, great. Current index is 2. Is 2 equal to 10? No. And now let's say the thing we're looking for, let's say needle is at index 2. So we say, okay, else if haystack at current index is equal to needle. Let's say it is. So this is true. So we return 2. So the method call, when current index was 2, returned true. Meaning it returns to the calling method, which was this method, except it was when current index was 1. So if the result of calling recursive linear search, needle haystack on 2 is let's say 2, we are returning 2, which means the return value of when current index is 1 is just passing on what current index 2's return value is, which was 2. So the return value for when current index is 1 is also 2. And then similarly, the return value of when current index was 0, which called current index when it was 1 and when it was 2, is just propagating the return value back to be like 2. Do I have a... Any questions about that? It might seem like scary, but you gotta flip that switch for recursion. Are we at the end? Yes or no? Is it the thing we're looking for? Yes or no? Otherwise, do the search on the remainder of the list, of the array. And then tell me what it is, right? To think recursively is almost to like think lazily. To say like, okay, I am responsible. I am responsible for knowing when current index is 0. I'm responsible for knowing if like what it is, what's the case for when current index is 0. Am I at the end? Yes or no? Is it what I'm looking for? Yes or no? Otherwise, I'm done. So I'm going to ask the next guy to tell me what it is when current index is 1. And they're going to get back to me. And whatever they get back to me, I'm gonna just pass that value on to whoever asked me to call it. Okay, am I wrong in thinking that the current index plus 1 piece is the I++ piece, but a little different? Yeah, it absolutely is. So let's think about this. This recursive step is like the loop part, right? Calling the search again, where you increment whatever the index is. This repeats that code while incrementing I. This base case here is the final thing right here. If we ever get to the end and don't find it, return -1. And then this case right here is the base case of, well, okay, we found it. Well, that's this part right here. This is the same algorithm. It is the exact same algorithm, just done with recursion instead of iterating. I can see how this is so much simpler. You just call a method again if the work isn't done. And that's kind of the spirit of it. Oliver Queen, wrapping your head around the nitty-gritty of the specific recursive algorithm is not trivial. But what you just pointed out is like the first step of magically getting it. Of like, look, either I find it or I don't. Or the next guy's got to find it. And whatever they come back to me with, because they're going to return a value. I'm calling this method again, but telling this person to look with the next index. So they're going to get back to me. They're either going to return -1 or some specific index. Regardless of what it is, I'm going to take the value that they give me and just pass it along to whoever asked me. So, are we at the end and we didn't find it? Did we find it? Return the value. Otherwise, keep looking, but someone else is going to figure that out on the next one. I'm going to see, maybe drawing this out will help here pretty good, I think. So let's say A, B, C, D, no, A, B, C, D, E, F, G. Okay. And of course, these have indices 0, 1, 2, 3, 4, 5, 6. Okay, so I'm going to keep track of a couple things here. So first let's say I'm looking for the letter D. Okay, I'm looking for D. So I'm calling search, pretend needle and haystack are some global things. I'm only going to reference the index here. So I'm doing search on 0. Is A equal to D? No. Okay, pardon me. Is 0 equal to the length? No. Is A equal to D? No. So the result of search on 0 is going to be the result of search on 1. So is 1 equal to the length? No. Is B equal to D? No. Okay. Well, now the result of that search is going to be whatever the result is of search of 2. So now, is 2 equal to the length? No. Is C equal to D? No. All right, so now I'm just going to return the result of searching on index plus 1, which is search on 3. Is 3 equal to the length? No. Is D equal to D? Yes. Okay, well, in that case, this right here is 3. So I found it. We just found what we were looking for. So I can return, right here, I can return the value 3. That's this part right here. If haystack is what I'm looking for, return the index. So I return the 3 to search of index 2. And then search of index 2, all that's doing is just relaying, because search on 2 to call search on 3 is calling that recursive one right here. Look what happens on line 8. That statement is calculate the result of this. This function here will return a value. And then whatever value this gets evaluated to, this function call, this method call, I'm just going to immediately return it. So I'm just like, okay, they told me a thing, and then I'm just going to pass that value along to whoever asked me. So search 2 now knows that, well, the answer to search 3 was 3. So search 2 now returns to whoever asked it what its value was. Well, just pass 3 along. Just pass 3 along. Just pass 3 along. So this would be the calling method. So now I know, oh, it's at index 3. Big old game of telephone. Exactly, it is a big old game of telephone. Except the good news is there's no data loss, hopefully. If we were to keep going, I'm going to do it in orange just to show the difference. And we're looking for like the letter Z, which isn't in here. Well, let's see what happens if we keep going. Well, okay, I do search on 4. Not there. On 5. Not there. On 6. Not there. On 7. Okay, well, search on 7 is, this is the length here. 1, 2, 3, 4, 5, 6, 7. Okay, so we get to search on 7. That's this base case, the one where current index equals the length of the stack. So now we return -1, meaning at no call of search before did we find the result. So I'm just going to recall that, where's my, there we go. This returns -1. This then returns -1. We play that telephone game. -1, -1, -1, -1, -1. And then the search of 0 returns that value to whoever asked it to do the calculation. So that's the idea here. Again, I want to emphasize we are just starting to learn recursion. So if you look at this and you're still like, what? you're fairly typical. That said, that is not me dismissing that like, oh, don't worry about not. No. If you don't get it right now, that's expected. Get it though. Figure this out. And you're only going to figure it out with practice. Okay? This right here is going to be critically important as we go forward. Recursion. And this is one of the this is a simpler recursive method, one of the simpler ones we'll look at. So it's a good place to start wrapping your head around it. When in doubt, remember, there is one magic trick in computer science when understanding code and whatnot, right? Everyone's always looking for the magic trick, and there is one, and people hate hearing it. The magic trick is follow what the code says. Don't make any assumptions. Do not skip a single line. Follow it out. And if you need a piece of paper and a pencil to do it, do it. One of the best investments you can make is buying yourself a whiteboard when working on assignments. If recursion is so horrible, why is it used? Because a lot of compilers will actually make it not inefficient. 2, mathematically, it is just as valid as iterating. It's more like natural in our universe recursion. And above a lot of those things is the simplicity of writing these algorithms. And when we look at trees, you're going to really start to see how the recursion's beauty pops up, because a lot of the algorithms we can write when dealing with trees are recursive. And they're the type of recursive algorithm that your compiler will like make more efficient. And writing an iterative version of all of those methods that we're going to be looking at with trees is disgusting. It's horrible. You don't want to do it. So recursion like makes it so we can very cleanly describe things. But if you're not familiar with recursion, if you haven't gotten enough practice, if you haven't had that switch flip in your head about getting used to recursion, it's not going to seem natural off the get-go. But sometimes, like, it's kind of what like Oliver Queen just said, is it's like, what is it saying? Is the current thing I'm looking for, well, are we at the end? Yes or no? Is the thing I'm looking at the thing I'm looking for? No. All right, hey, you, keep looking on this list, but start at the next one. That's the idea. Is think of it in terms of like delegating. Okay? If it's not here, well, it's either here or not here based on the remainder of this list. So if I didn't find it and I can't conclude that it's not there, someone else has to do that. And whatever they do, they're going to tell me, and then I can get back to you. Think of it in terms of the like how many students are in this line, right? Well, it's 1 plus however many are after. How many are after? I don't know. They'll figure it out though. And that's the recursion right there. Are we at the end? Yes or no? Is it what we're looking for? No. All right, well then you got to tell me if it's there or not. Well, how are they going to do it? Well, it's the recursive call. They're just going to follow the same thing. Are we at the end? Is it what I'm looking for? No. Okay, well the next guy's got to tell them whether or not it's there. So, as a note, and this is a very common pattern you'll see, so this is the general recursive one. But of course, if you ever wanted to do a linear search on some array, you're going to want to start at index 0, right? So every single time you call recursive linear search, it's going to be, okay, your needle, your haystack, 0, which might feel a little silly. So like if I want to call this method, I need to start it with current index is 0, so like this. But it is remarkably common to write what we would call like a little helper method that makes the first recursive call with the proper values. So what I would do is I would like overload this method, recursive linear search, but have it where I don't specify the index. And if I don't specify the index in the parameter list here, it like that one means, okay, just call the other one, but start at 0. Because imagine like I had a bag, right? Some indexed bag data set, right? And I wanted to do a linear search on it. And my linear search, it wasn't iterative. I wrote a search that was recursive. It'd be kind of annoying if like the interface for that bag had the current index in the parameter list, because what am I searching through? I'm searching for a needle in a haystack. That's what I want to do. The current index is more of an implementation issue. So I would make the public one, this one that takes a needle and the haystack. And then I would probably make this one here private. So you can't call this directly from outside the class, but this one here would call it. Don't worry, we'll see examples of this once we get to the trees. Okay, this may seem quite different from the iterative implementation, but take some time to look at the code and see what's happening. Start is current index at 0. Are we past the end of the array? Is the element what we're looking for? Otherwise, if we're not at the end and we didn't find it, do it again, but check it on current index plus 1. It's the same algorithm. It's just written differently, but the algorithm is the same. I'm willing to bet that if you had a stack of paper, let's say you had a stack of exams that weren't sorted, all right? And I said, hey, look for student so-and-so, look for student Bob Smith in that stack of exams, okay? Are you, here's what I'm going to do in my head. Look at the first thing. Is it what I'm looking for? Yes or no? All right. Do it again, but on the next one. Is this what I'm looking for? Yes or no? Do it again, but on the next one. That's recursion. It's just, you don't have to think about it as recursion in real life because you didn't explicitly write it down. Because recursion or iterative is like the syntax. It's the writing of what we want. The algorithm is the linear search. The specific implementation of it is did you do it iteratively or recursively? When you are doing things in real life that require looping, doing processes over and over and over, you can't even really say that you're doing it iteratively versus recursively because the spirit of the algorithm, that's irrelevant. I'm trying to think, what are other processes we do? The searching through a stack of exams is a simple example because we've all had to do that before, searching through something. So the process, it's recursive in the sense that is it what I'm looking for? Yes or no? If it's no, do that exact same thing again, just on the next one. How? A loop or recursion? That question doesn't make sense for real life. So why to learn how to do things iteratively in the course first before recursive, if it's much simpler? Because chances are that you raise a good question. In fact, almost all universities will teach with iterative stuff first. But at some universities, they start with functional languages that are going to be recursive only, where there is no such thing as loops. So there is an argument to be made for starting you out with functional recursion only. There really is an argument there. Realistically, iterative is, because a lot of times when we're doing loops, when we start learning about loops, I want to do something 10 times. And a for loop is really easy to do that with, right? Where once you start to get to problem solving, where it's I want to look through this list of arbitrary length to see if something's in there. Well, you're already familiar with the for loop, so let's continue with that. Now let's look at it with recursion. But yeah, there is a strong pedagogy argument for starting with recursion. And you're right. Maybe we should. I think it tends to feel like iterative is simpler because it ends up being more, I don't want to say explicit, but it tends to be more follow the steps. You know, when I'm looking at the code, if there's a loop, okay, it loops until it's done. Like, it's kind of easy to follow the lines of code, where if you have all these recursive calls, you end up having to like nest the calls inside themselves, which can get a little overwhelming, I think, to new programmers. But yeah, I think iterative felt a little more natural at first because we started with Python and learned there for sure, absolutely, yeah. All right, so that was it for a linear search. But let's say you're looking, I think I did this in 161. So if I did, the fun's already spoiled. Let's say you're looking at page 554 in a textbook. Or pardon me, you're looking for page 554 in a textbook. You've got this giant textbook, okay? And what you're probably gonna do is you're like, okay, I don't know. I don't even know how many pages this textbook has. So to start, I'm gonna open this book somewhere in the middle. Like if I'm looking for page 554, do you open the first page of the book and say, oh, this is page 1? Is this the page I'm looking for? No. I mean, you would do that if you're looking for page 1, but if you're looking for some arbitrary page, you're gonna wanna take like a guess as to where it would be, right? So I'm gonna guess somewhere in the middle, and I open my book, and I'm looking at page 383. Meaning, I'm looking for page 554. So I've opened my book, and I've got 383 pages over here. The pages 1 through 383. And I have the pages 383 to whatever. I don't know how long this book is. But I've got pages over here that are 383, 384, 385. Which half should I look at next? The pages 1 through 383 or the pages 384 plus? Which half do I look at? This isn't a trick question. Which half? All the numbers less than 383? If I'm looking for 554, am I going to find 554 between the numbers of 1 and 300 and whatever? Yeah, exactly. Higher. We look at the higher half because I know that the page 554 is not less than 383, meaning it can't be between pages 1 and 383, right? So if that happens, I'm immediately able to, like, let's say I have a book of 1,000 pages for easy math here. The size of the book is arbitrary, but if I have 1,000 pages and I split it 383, and I want to keep searching, if I know that the thing I'm looking for is in one half of the pages after I split, I use the word half, one segment, I split it in some way, not half if there's 1,000 pages, but 383, I'm able to throw away 383 pages. I don't need to look at those 383 pages anymore to find what I'm looking for. I was able to throw half of them away. Half. Where if I started at the beginning, if I looked at page 1, am I going to go, oh, is that page 383? No. All right, keep going. Well, now I have 999 pages to look through. I eliminated one page if I start at the beginning. Where if I start by kind of like opening it and going, I'm at 383, I can conclude that what I'm looking for is like on this side of the book, not this side of the book. So I can now eliminate all of those because I know it's not there. So if with the linear search, if I look at the first page and I ask a question, is this what I'm looking for? Yes or no? All I can do is eliminate one page with that answer. Where if I look at 383 and I'm answering that question, I'm able to answer a lot more. I'm able to get a lot more information. And that information is, it must be over here. I can throw away a lot of information. I do not need to search pages 1 through 382, I guess. I do not need to look through all of those pages. I get 383 as well if we're counting it. I do not need to look at any of these 383 pages for the page 554. I'm able to eliminate all of them. That's a lot of work I just ditched. Where if I'm doing the linear search and I start at the beginning, page 1, yeah, no. Page 2, yeah, no. Page 3, yeah, no. No, that's a stupid strategy. You wouldn't do that. I'm willing to bet if you had a textbook in front of you and I said turn to page 554, you're not opening it at the beginning of the book and you're not turning page by page looking for 554, right? That's a ridiculous thing to do. You wouldn't do that. No, you would go like this and then you'd thumb this way a bit, thumb that way a bit, and then you find what you're looking for. This is the interpolation search. So since 554 is greater than 383, it must be in the set of right pages. And we are able to eliminate 383 pages from the set of left pages from our search, since 554 must not be in there. So next, okay, so you've got 383 over here. I'm getting all mixed up here. I've got 383, and the end of the book, at the end of the book, and see page. Okay, you turn to a page somewhere. Here we go. I now turn to a page somewhere between 383 and the end of the book. And I open that page and I see it's page 621. Okay, so 383 is here. Let's go back to Paint. Let's say I have 1,000 pages. All right. My first guess was at 383. I'm just going to put it here. Okay? Meaning, we were able to eliminate all of that. So my next guess, I was able to, and let's say this was page, I'm going to write page 0. 1,000 for easy. This is 383. Okay, so my next time I look, I'm looking through pages 383 to 1,000, right? Because I don't need to look at these ones. And I turn to page, where's my red? 600, what was it? 621. So this time I turn to page 621. Right? Nope. Let's make that black. 621. It's not so much randomly, it's like, picture a book and I'm just kind of eyeballing like, this is, I don't know, maybe around here. And I just happen to turn to page 621. I'm looking for 554, I believe, is it? 554, yeah. Okay, great. So now, the second time I made a guess, so this was my first guess, 383. The second time I made a guess, it was 621. And I'm looking for 554. Is 554 going to be over here? No. So I'm able to eliminate all of this and continue my search only on this part. So you would need to know the length. Well, yeah, I've got a book, right? So I can see the end. Yeah. So the next time I'm going to make a guess, is it's going to be somewhere between 383 and 621. And, you know, the difference between 621 and 383 is a heck of a lot less than 1,000, right? So I have a much smaller thing to search through. So what's my next guess here? Oh, I guess I don't really have a next guess. So my next guess, maybe I turn it to page 540. Okay, so my next guess is 540. Oh, hold on. My next guess is really between here and here. So my next guess, I pick 540, which is like here. Okay, great. So now I know this isn't there. It must be on this side because 540 is less than 554 and so on. So I keep like taking steps towards what I'm looking for, but the steps I'm making are much bigger than one. Because with the linear search, every single time I ask a question, I can eliminate one thing. With this type of strategy, I'm able to eliminate a hell of a lot more than just one thing. I'm able to eliminate 383 things here. So this is the strategy here. And I know you have all done this. You have all done this before. So this right here, this idea, is the trick behind something we call a binary search. The idea is, what do I have? If we are looking for the number 11.5. Okay, yes. So, if I'm looking for the number 11.5 in this thing right here. Now, imagine this is an array. This is an array. Picture this as this right here. Copy image. Okay, and then copy image. So I'm representing the exact same information, but I'm drawing it slightly different. Oh man, I heard, why do I? Oh, because you thought there was a mistake. Yeah, okay. So, this is the same information. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But I've kind of represented it as like, well, what's the middle between 1 and 15? Well, let's say it's 8. And then what's halfway between 1 and 8? And what's halfway between 8 and 15? And what's halfway between 1 and 4? And what's halfway between 4 and 8? You know, that's kind of what I'm doing here. So if I'm looking for the number, and pretend this is sorted here for a second. If I'm looking for the number 11.5, I would have to go look at, okay, is this 11.5? No. 11.5? No. 11.5? No. 11.5? No. Is this? 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 No. Oh. And I guess around here I can conclude, because I see 12, and I know 12 is bigger than 11.5. So I guess I can conclude it's not there. So I'd have to go all the way down here. Where now let's see if I'm looking for 11.5. Okay, is 8 11.5? You know, I went halfway. No? All right, well, let's go halfway between where I am and the remainder. Okay, well, that would be 12. Okay, this 12. Okay, no, 12 isn't 11.5, but 11.5 should be less than 12. So I know that it's got to be between the 8 and the 12. So let's go halfway between the 8 and the 12. I guess that's a 10. So we look at the 10. It's not exactly halfway, right, because integers. So now we look at the 10. All right, well, it's got to be greater. Now we look at 11, but we're at the end. So there must not be an 11.5. So where here I had to go all the way down and look at 12 things. Here I look at 1, 2, 3, 4 things, which is way less. And again, notice that every single time I make a guess, I am able to take this chunk right here, when I look at 8 and go, is it left or right? Well, it's on the right. Okay, well, we can ignore all these numbers. 12, is it left or right? Well, it's left. So I can get rid of the remaining half. 10, left or right? I can get rid of the remaining half. 11, well, we're at the end. Where when I go down, is 1 what I'm looking for? Yes or no? No? Okay, I can only get rid of one thing. 2, no. 3, no. 4, no. And so on. So the magic with this strategy is being able to throw away half of the crap we don't need. So the complexity analysis of binary search, we're going to look at. The trick is to not overthink it. Well, I guess we won't get to it today, but when considering linear search, if we want to look for 11.5, there are a total of 15 things. I guess if we want to look at all of them, we're going to look at all 15. But with the binary search, we'd have to look at 4 things. We get away with looking at fewer things because we're ignoring half the remaining elements every time we continue our search. 11.5 is greater than 8, therefore we can ignore all elements on the left side. Yeah. Any idea what the relationship between... Okay, this is where we'll pick up next time because we are out of time. But this is where we'll pick up next time. And we'll talk about this, implementing this binary search. Would the tree look different if there was an even number of things? Why don't you draw it and let me know? I mean, it would look different-ish. And the tree would look different if the numbers aren't sequential either. Like if you've got like 1, 7, 11, 12, 44, 45, 52, you know, like the numbers don't necessarily need to be like contiguous like that, but they are sorted. Anyways, I'm going to stop the recording because that's it.